是在你那个上面吗？不是，是那边你刷。
我们听，Are you ready？
OK。
Alright。
你们没有？
有了，过了。
Okay, let's begin with the challenge process. Opponent team, please choose a problem.
Okay, we first challenge problem 15, wet straw.
We reject.
Okay.
15 rejected. You only have 2.
Okay, we challenge problem 2, droplet microscope.
Droplet microscope. Problem number 2.
We accept the challenge.
Okay. Problem number 2, accepted. Please prepare for the report. And also write down the name of your opponent and reviewer. Problem number 2 has been accepted for
不好意思，你们有没有那个 Type C 的那个充电可以借一下？
我看一下。
有吗？平常是，我是可以放在这里充吗？还是你你有这个是你有充电器？那我可以借一下。那我那次看有没有充看看，一起去看。
Reporter, please begin with your report.
Honorable jury and fellow computers, I'm Sam from Team Alpha's Children High School, and I'm going to report the problem 2, droplet microscope. The problem statement is by looking through a single water droplet placed on a gas surface, one can observe that the droplet acts as an imaging system, and we need to investigate the magnification and resolution of such a lens. And so our main focus, we have two main focus. One is how to observe the magnification and resolution of water droplets. The other one is, does the size of water droplets affect the imaging system? This is our content. We have the observation, theory, explanation, and conclusion. Then is the observation. We put a water droplet onto the iPad surface, and we can see there have some RGB lights into the water droplet. So we look closer. We can see there are some pixels. We can see clearly. Yeah. So the qualitative explanation is we consider water droplet as a lenses, and the reflection effects can make the pixel in the iPad enlarge the distance between each pixel. Then turn to the theory. The first one is a lens equation. The lens equation has two forms. The first one is a Gaussian form. It is 1 over RO plus 1 over RI equals 1 over F. And this is just a screen. Our object and image is both sides to the droplet. So it must be the RO must be closer to the focal length. Yes, and R is the average radius of droplet. RO is the distance between droplet center and object. Our object is a pixel, and RI is the distance between droplet center and image. The image is a magnified pixel, and F is a focal. Then we use the lens equation turned to the Newtonian forms. It's x out, we find the xi is equal to f root f, yeah. And xo is xo is object to the distance to the focal length. Ri is image to another one focal length. And our RO is smaller than the focal length, so we make it coordination, and length is 0, so this is minus x. So then we can make this form. The f minus RO times f plus Ri is equal to f the root of f. Then the magnification can represent the h over the small h over double h. The small h is the image distance, and big H is our normal times, and it's equal to Ri over Ro. So we can get the Ri is equal to Ro times M. So we can put into length to get Ro is part is line, Ri is this. The next one is let's make an equation, and it's 1 over f times n minus 1 times the curvature, and the radius of curvature, and one of the curvature is horizontal to the screen, so it's infinity. So turn to the curvature to be 0, so we can get this one. The resolution. The resolution is can get this one. So the lambda is a wavelength of light, and NA is a neural aperture. It can also be n sin theta. The n is a reflection index. Okay. Due to the lambda is the same and n is 1.33. Yeah. We put into length. We discover the R and F have no correlation. So it's an experimentation. We put the pipette to drop the same volume of the water droplet, and we put two kinds of the picture. One is a front picture and a side picture. Front picture is to discover the magnification, and side picture is to find the curvature. So how to calculate the magnification? First, we fix the picture score in our picture, then calculate the length of image. Because in the iPad screen, the pixel in the iPad is one is this millimeter, and we calculate the length of image. We multiply length, can get the magnification of what the droplet. Then, if the droplet has a hemispherical, also the contact angle theta equal to, and we can get the R is equal to this. But we can make the droplet very good. So when we can use that to find our curvature. So how do we use get the curvature? We also fix a picture score and measure the length to making a measure in the decimals. We can get the curvature and length. So the first extent is the radius of the droplet. So in this picture, we can find the radius and magnification is a negative correlation, and because variance and radiation is a negative, is a positive correlation. No. So we can get the radius and negative is a negative correlation. The next one is a variance of the droplet. In the theory, the contact angle is 90. And okay, our variance is 5, 10, 15, 20, and 15. And you can see there is not very so we think it is the contact angle is too small. Yeah, it's a little small. Then it's a calculate resolution. Like we can see it, the spherical is in experience is fit to the theory. So the conclusion, this is a problem statement, and we can get the our conclusion is the droplet value to the magnification is negative correlation, and the contact angle to the magnification is positive correlation, and the value to the resolution is no correlation. It's our result. Thanks for your kind attention.
Okay. Opponent.
Okay, so first question. Do you consider your droplet to be a sphere shape or an ellipse?
We can control its value.
I mean, like, do you consider it a sphere shape or an elliptic shape? Okay, we can go to the next question. Okay, second question. Do you consider the acceptance angle of the droplets?
Yes.
Okay, so you use that in
To calculate conversion.
okay.
Like this. We put we know the distance and height, so we make the
Model.
model now.
Okay, okay.
And together.
I understand.
Yeah.
Okay, third question. Do you consider the lower part of the droplets? Like, you can observe the shape of the droplet curving inwards when at lower volumes. Do we consider that part to affect your results?
No. Because we contact the angle is smaller to an 90 degree.
Okay. Okay, so now next question. Do you consider the distortion of the image formed by the droplets?
Yes.
Okay. And okay.
Okay. So prepare for the report and discussion. Component, please begin with your
Okay, so I'm Ethan from Team MD Fresh, and I'm going to be opposing the problem to droplet microscope. Okay, this is a problem statement, and their main focuses are, first, how to observe the magnification and resolution of the water droplet, and second, does the size of the water droplets affect the imaging system? And I think their advantages are clear presentation and clear experiment setups. And our suggestions are clear notations of the content, like theory and on a diagram. And second, definition of the shape of the droplets. And the summary of the reporter, in the theory, they use the lens equation Gaussian form and the Newtonian form. And for their setup, they use pipettes with the droplets and observe the pixels on the iPads and calculate curvature and magnification. For parameters, they focus on the radius of the droplets, the volume of the droplets, and calculation of the resolution. And these are the points of discussion that we're going to be doing in the discussion session. And first, we're going to be defining the shape of the droplets and how it will affect the resolution and magnification. And second, how to define the curvature and which part of it the curvature represents. And third, the lower part of droplets, because it's obviously like a phenomenon it can be observed when doing an experiment. So I think it should take into consideration. And fourth, the focal lengths. There are like multiple equations used to calculate focal lengths, and we're going to be discussing that. And fifth, the calculate method of magnification. And I want to see that, and we'll be investigating in how like the other parameters, the other factors such as like focal length affect the magnification. And sixth, we're going to be considering the evaporation rate, which is quite important when you're conducting an experiment with lower volumes of droplets. And number seven, the changes in resolution, because I believe the focal length is involved in calculating the theta, so I believe there might be changes in resolutions. And eighth, how to define the contact angle. And thank you.
Please begin with the discussion.
Okay. Okay, so let's talk about the resolution first. Okay, please turn to the page when you're defining resolution. Okay, so the first question is, what does the 0.61 represent?
It's it's a constant.
Constant of like what?
To represent resolution. It's
Okay, so let's move on to the next one. And for the sine theta, I wonder how you calculate the sine theta.
okay. Then you can see there is a sun. The more clearly the pixels. So it's left and left some clearly pixels.
Yes.
And we find the way distance and our curvature is to be there. So it's the effective effective G-set to our theta.
Okay, so could you turn back to the previous page? Wait, next one. Actually, next one. Next one. Like where you define the resolutions again, like the equations. Okay, so from this graph, my understanding is that so this is the vessel and this is the water droplet you're observing. And from this graph, there are like two sines thetas, and the ones that you're observing right now and on the diagram is a flat circle. And do you think like when you're like calculating the resolutions, does it like affect your calculating methods? Like it's like you're like starting from the flat surface, but like when you're explaining, you're saying that it's like it starts from there.
No. The thing is trying to layer, and the our object is in layer. So this is our surface, and is layer. So yes, this is our photon, and this is theta. So we come to layer to reflect the image.
But I think the theta means it's actually the acceptance angle because it okay, so it's probably gonna start like this, but what does that blue circle represent? Is it a pixel or like the entirety of the droplets?
It's like a normal length, and layer is effective radius, but in the droplet we can see there are some somewhere it doesn't very clearly, so it's not very effective. So we can use the like this x. We can use the z equal to 0. We can use there to calculate that.
But the definition of the acceptance angle is like how much the angle is like how much your light can actually goes through the lens.
Yes.
So for example, if your lens is like this and this is your light source, this is your acceptance angle. So therefore, I would say I suggest you using like the entirety of the droplets to calculate the solution, because if you are just only taking into consideration of the clear ones, then you are probably misunderstanding the concept of the acceptance angle. Okay. So regarding this, I also have another question. In your conclusion,
Yes.
you said that focal length has no obvious correlation with the resolution.
Yeah.
But from your explanation in this, I can see that you use focal length in calculating your resolution, your theta. And how do you explain that?
Okay. Then come back to okay. You can see there, and this is the theta. Because we know the focal is in the lens vector. We know f is equal to 1.33 equals r, right? So we make that put into the by f. So the r will be cancelled out. So the f would be cancelled out. So our r doesn't have the correlation with f and r.
So you said they are cancelled out.
Yes.
Okay. Okay, that's
I think.
okay. It's alright. Okay, next question. Okay, I want to clarify something first. Is when you're stating your theory, you said that you calculate the curvature,
Yeah.
and let's say this is your droplet, and you like point out like which point of the curvature it represents.
Yeah.
Which
Okay. Okay.
Is it the
This is a waiting surface of light,
yes,
and that's maximum radius.
yes.
Yes. So in this picture, I said I only find the most effective ways. Yes, like X and Z only find the most. Yeah, you can see.
Yeah, you use the most effective
Yes.
image to.
To-
But like my question is that like your curvature used, like what does it represent? Like, is it this point, or either this one? Which one is?
In the same height, only is this one and this one.
Okay, so what about the front ones?
It doesn't impact because like lens and this, and your photo first step you will go horizontal to the lens. So this one is there. So it and yes, the image like this.
But in the definition of the lens vector equation, you can see that it uses radius, right?
Radius.
And that radius is related to the curvature, but like how do you like link those together?
The radius, the arc is not the
It's the radius of
it's not the box and it's the radius of curvature.
yes.
Yes. So it's equals to like this. Our curvature is 1 over the radius of curvature.
What does this represent?
1 over the
Oh, you mean is this curvature, right?
Yeah, it is
Oh, okay,
curvature,
curvature.
curvature.
Okay, it's alright.
Yeah.
So, because can you turn to the page that you said about the lens vector equation?
Yeah.
Okay. So, what does R1 and R2 represents on the droplets? Like, what is R1 and R2? We can just use it to make sure.
So for the lens, we have for lower lens we have 2 side lines.
Yes.
Yes, and both sides have this curvature. But
Yes.
in the water droplet, we have third one. So this side is horizontal to the screen. So it's
It's close to infinite, so you
Yes.
discard it. Okay.
yes.
Then, so your R2 is discarded. So therefore, your R1 represents the top of the droplet.
Yeah.
Okay. Next question, I'm actually going to be discussing. About your first experiment, page 20.
Okay.
Next page, please.
Next step.
Wait, previous purpose.
This one.
Previous one.
This one.
Yes, okay. So, as you can see in the diagram, let me point this out. So, this is all the same volumes of droplets, right?
Yes.
But like, why the magnification of the same volume of droplet differ?
Because to a droplet, we can say this is our like this is a radius, right? So for one, we have this like the more our contact angle to be more bigger or smaller one. Yeah, like this. So it will affect to our arc in droplet. So because contact angle could cause our curvature. So the magnification would be different.
So therefore, you don't have like an actual number for like for each volume. Like it's just a scatter of numbers, right? So that means the experiment probably needs more accurate like setups. Okay. And I think the time is up. Okay, thank you.
Go on with the summary of your discussion.
Okay, so we first talk about the shape of the droplets, and the reporter considered it to be a sphere, and also we talk about the lower part of the droplet, which occurs when the droplet is at lower volumes, but they didn't think that would affect much of the magnification and resolution, so they didn't take that into consideration. And also we talk about the curvature of the droplets and how the focal lengths correlated to the resolution, but they say the focal length is like divided, so therefore there's no focal length. There are no relation between the focal length and resolution. And then we talk about like why the same volumes of the water causes different magnification, and they said that there's no like clear explanation for that. So therefore, I think there's some room for improvement for accuracy. Thank you for listening.
All right. Now let's have a reviewer to ask questions.
Alright, so the first question I want to ask the reporter, so in page 12,
Please come.
so you mentioned that you defined the resolution, right?
Yeah.
So which kind of resolution?
This kind of resolution is
So there are image resolution and optical resolution, right? So which one did you use?
I think it's image.
But in this part you use the formula of the optical resolution. So did you consider it? Fascinating. So how about the opponent?
Yeah, it's like the equation is for numerical curvature, right?
Yeah.
Okay, so that's for optical lenses, and I think they use the sine theta and the focal length, so yeah, it should be optical lenses.
Okay, alright, so turn to page 50. Yeah, so do you agree that it needs to be explained with the image resolution?
Yeah.
So how about you?
Pardon? I didn't.
So in the page 15, he uses this pixel to explain it, and so he needs to use the image resolution to explain it, right?
Yes.
Alright, so thank you. And so next question. So you use iPad to do the experiment, right?
Yeah.
So do you consider that there are different layers of the iPad?
Yes, I know. So I control the stem and we put accurate.
But in your lens maker equation, so the lens maker equation. So I think in the equation that you only consider that there are only one layer, right?
Yes.
So do you consider to like maybe modify it?
Yeah, it could be modified.
All right. So how about the
Okay. So for iPad, it doesn't have multiple layers. It doesn't have multiple layers at its original form, but if the user applies more together, it would be like probably modification to the light rays. Therefore, it might affect the resolutions and the other factors of the imaging effect. So therefore, if the experiment is done in a perfect form, therefore, yeah. Okay.
right. So please turn to page 17. So why do you model it as a perfect curvature? So in all of the experiment, is it perfect? So please give me a yes or no answer. Is it all perfect in your experiment? Because you model it as a perfect curvature.
Yes.
So yes for all the experiment.
The time is up. So please prepare for your report.
Alright, so this is a reviewer from Team Excalibur, and today I'm going to review problem number 2, droplet microscope. So by looking through a single water droplet placed on a flat surface, one can observe that the droplet acts as an imaging system. So we need to investigate the magnification and resolution of such events. So the theory, he uses resolution and Newtonian form and focal length, which uses length-maker equation and Gaussian law to do the explanation. And the experiment part, he uses only one parameter, which is the volume of the droplet, and he has set out an iPad controller. So the strength, I think he had good qualitative phenomena explanation, and he has a clear set-up picture and has some simple physics explanation. But the suggestion is that he lack of comparison between the theory and the experiment result, and lack of explanation for the experiment result. And he didn't consider about the shape of the droplet, which is a curvature. And he uses optical resolution, which should be using image resolution because he uses pixel to explain the theory. So, and this is a summary of the opponent. So he asks about the definition of the curvature and the focal length and the way to calculate the magnification and resolution and the evaporation rate and the contact angle. And in the experiment part, he asks about the way to drop the water. And I think he asked about some details in the theory, like acceptance angles, and he pointed out some problems in the experiment setup. But I think he's not clear about the concept of resolution and magnification because he didn't say that which resolution should be used in his discussion, and in his discussion during with the reporter. So the opponent asked what is the concept 0.61 mean in the equation, and how to calculate the sine theta in your theory. And the reporter didn't say much, but he said about something like using the pixel. And I suggest that the reporter should define the constant more clearly. And from page 12, how do you calculate the correlation between R and F? So the reporter answered that it will cancel out, so it will affect, which is very weird. And I think that because it will not cancel out, so we suggest reporter to clarify the meaning of the formula. And the reviewer asked about what type of resolution do you use in your theory, and the reporter said that image resolution, and the opponent agrees. And but the image resolution, but reporter only writes about reporter uses the formula of the optical resolution to explain the image resolution, which is not really adequate. And about the setup, so do you consider the multi-layer of the screen of the iPad? And the reporter said that he only considered one layer, and the opponent said there is no multi-layer. And I think that because the iPad had a few layers before the screen, which is the protection layer and the heat deprivation layer before the screen. So actually he needed to use the modified formula of a lens maker formula and both resolution and for magnification. And so I asked about that, did you consider that the drop is a perfect shape? And the reporter said that yes. And so I actually asked about when it's in the experiment part. So he modeled it as a perfect curvature. So is it like very accurate at all? But I think that because he modeled it as a because in the experiment he didn't mention that with how they control the shape. So I think it's not feasible to use a perfect model. Thank you.
So let's now have reporter having his concluding part.
Thanks to the opponent and reviewer, we know the focal. We have to have a focal conclusion and theta, and then it's a resolution comparison because we don't know. We use the wrong resolution theory, and then it's use the same layer. And we use the same layer like the iPad. And it's a continuing market is the clarify of the discussion. We consider the droplet as half of the oval, not square. Then if we draw the thickness not, but the upon just the thickness, but actually it's we consider the thickness, and the same value will not have the same shape. It causes different magnification, and we have to include some point is the curvature, calculation of the resolution. Thank you.
Okay. Let's move on to the question session. Any questions?
Before, could you show your definition of resolution? Yes, this formula has a name. You know the name of this formula. Will you say that? Okay, your time's up. Opponent, do you know there's a name of this formula? Do you know the name?
The name of this formula.
Yeah.
Okay, so I think this is
So you
the.
understand the principle of this formula?
Pardon?
If you understand the principle of this formula.
Oh, because I read it and it's actually like the D equals to the later part of the formula. So and D represents the solution of such imaging pictures, and therefore we use numerical aperture to define the resolution.
Alright, so I believe he uses Riley's criterion to, and it's about to, and its meaning is to calculate the optical resolution.
Calculate optical.
Yeah, optical resolution.
No, no, you are correct. This formula is the theoretical limit of resolution, theoretical limit of a perfect length. And none of your experimental can reach a perfect length. And this is theoretical limit. Alright? To do your experiment, you should Google, just call knife edge method. How can Part? That's the experimental method to define, to determine your solution. Right?
Okay, let's move on. Any other question from the viewer?
Question for the reviewer. So when you talk about layer, what do you mean?
Alright, so I use my
Yeah.
So about the layer part. So this is an iPad, but an iPad can be I think it can be divided as 3 parts. So this is the first part is the protection layer, and the second part is the heat deprivation layer, and the third part is the screen. Which is where the pixel at.
Are you talking about the screen or the lens?
So this is the screen, but up to the screen there are still 2 layers more. In an iPad. Yeah. So the pixel is right here, but in his formula, he only uses 1 layer to. His formula only contains about like the calculation of 1 layer. So I consider that he should do the multiply of the formula.
But you think the resolution will be affected by the top 2 layers?
Yes.
How? How is the resolution affected by the top 2 layers?
So. So it would have a refraction of glass. So it counts kind of as a glass. So it may have the refraction, like extra refraction. So it's like an extra layer, and they have some refractions to calculate.
Any other question? I have a question for the reporter. On page 8 of your slide, it seems that the image and the object is on the same side of your lens. But then how do you observe your image?
This technique to watch because image will we can watch that on top of.
Okay, the time is up. So let's go on with the grading.